Okay, so let's start. Let's, let's get started. Yesterday, actually, before I start with today's lecture, on Monday's Veterans Day, so it's a school holiday, so there will be no class on Monday. You can still come to campus if you want, but I don't think there are any classes on Monday. So no lecture as well. I will release the last year's midterm too as well, so you can practice it for our second midterm on the following Monday, which is going to be on the 18th. Um, so today we're going to finish lag compensator and move on to PID and lag lead. A recap on lag compensator design is that it's similar to PI controller design where we place a pole near the origin and then a zero to the left of it. So you want your zero to be higher in value if you take the magnitude of it. That's what causes lag delay. It's going to make the system have a little bit more delay, but yeah. The nice property about that is that we can reduce steady state error based off of the ratio of the zero divided by the pole. But we can't make steady state error go to zero. We can only reduce steady state error. And yesterday I derived briefly what it does. Assuming that our gain remains the same, then the amount of error reduction we can get is achieved by the ratio of the zero and pole location. And basically, what you want to do is you want to choose your pole location and then choose the corresponding zero that is to the left of it to get that reduction in error. So to show that in an example, yesterday, we started the lag compensator design and we wanted to reduce steady state error by 10 times with a damping ratio of 0.5. So the first thing we did was we found the uncompensated closed loop pole and the corresponding gain for that. Then from that, we were able to then find the steady state error of the uncompensated system. And then next, we calculated what the 10 times reduction would look like. And then from that point on, we could then calculate the ratio of our pole and zero needed to get that reduction. Are there any questions? Okay, so we wanted our steady state error to be reduced by that much. So we had 3 over 16 for our steady state error. And then we found that, well, compensated system needed 3 over 160 to be 10 times reduction. So then we found the new KP compensated constant, which is defined here. And then next, what we want to do is we want to, apologies. Next, we want to find the compensated pole and zero. So what we do is we choose a pole close to the origin. Fine. Compensated PC and ZC. So we can just arbitrarily choose a pole close to the origin. And from there, we see that we can then just plug it into this equation here. And we get ZC over PC, which is 0.01 multiplied by KPU, which is 13 over 3, is equal to 157 over 3. So then when we calculate this all out, we can find that ZC is equal to 0.121. So then our compensated system, and this is going to be of our open loop transfer function. C of S, G of S is going to be equal to, it's going to be 13 times S plus 0.121 divided by S plus 0.01 multiplied by our original system, which is S plus 1 times S plus 3. Any questions? Note that we use the gain from our uncompensated system. And the reason why we do that is because a lag controller, it's going to more or less retain the shape of our root locus. So we're not changing the root locus shape, though that's not our objective. So because of that, we can just choose the gain from the uncompensated system because the gain or the root locus of the uncompensated system has a similar shape. So we choose the gain and we use the uncompensated gain from that root locus and it'll be a similar pole value.
Is that 0.121? Why
Oh, yeah. So we define, yeah, so ZC is 0.121 because we define it like this. So we define our controller as S plus ZC divided by uh, S plus PC. So the actual zero is going to be minus ZC. Yeah, the pole is going to be minus PC. There are textbooks that also define it as this, and I actually think this way makes more sense, but because it's not as common, I go with what I see is more common. Zero is Z C and pole is PC. So because of this notation, I guess it can be confusing because we say ZC, oh, that sounds like the zero. It's actually negative ZC, but this is more common. But the bottom one is also not uncommon though. Just use context. Um, that's also why I like to write it as the absolute value here. Even though it actually doesn't matter, but it's just more to, I guess, a self reminder to myself. I don't think the textbook writes it like that. It's a reminder to myself that we're always looking at the larger value, the magnitude of the larger value. But I always think of it as is the zero to the left of the pole or is the pole to the left of the zero? Because that's all we care about is how like the poles and zeros position relative to each other on the left half plane. We don't want to put the controller stuff on the right half plane ever. So maybe I'll just be a little clear here. I'm just going to write C of S as S plus ZC divided by S plus PC here.
range of realistic PC values that we can choose?
Yes, there is. It's going to be limited on your hardware limitation. So the question is there a range of like realistic PCs? So, oh, it's actually in my next slide. So I was going to show you a MATLAB that like, or I was going to show you the MATLAB of this, and I'll do that after then. So here, here's a lag compensator in an analog electric system, and you can see that our PC that we can choose is dependent on the resistor and capacitance value here and alpha. So that's dependent on the resistors and capacitors available that you can wire up. Um, in digital systems, I'm not exactly sure, but if you have a digital system, that means it's powered. So we could just use a PI system and take the integral or approximate integral. But let's say this is before digital systems. This is how we would do that. Okay, so I'm going to code this up in MATLAB, or I already have the code available. Yeah, I'll just show you. Okay, well, I don't have it open yet. All right, so let's go to the lag demo. Oh, there's multiple demos. Lag compensator. There you go. All right, so this is our example that we just did. And we found this is our transfer function of 1 divided by s plus 1 times s plus 3. So then this step, basically just find the root locus, and this is our uncompensated gain. So if I to run it, and all right, so I now have the root locus of the uncompensated system. Looks similar to the drawing we did. And then now we added a pole at 0.1 and a 0 at 0.121. And then I define my lag compensator as this. So S plus ZC divided by S plus PC. If I wanted to be exact on my root locus plot, I could choose the appropriate lag compensator gain, but we're not going to do that. We're just going to stick with 1 because we're going to use the K from earlier, 13, because our root locus should more or less be the same. And then I'm just going to run this section and show you the difference. We should see a 10 times reduction in steady state error. Our original calculation was steady state error was 3 over 16, which I actually do not remember off the top of my head what that is. 3 over 16 is roughly 1/4. It's shy of 1/4. So that looks about right. Let's see. 3 divided by 16 is 0.19. And so yeah, that makes sense because right here, if we look here, our red is our uncompensated system, and that if you look here, we are, yep, that's roughly 0.19 an error, and then we should have a 10 times reduction, meaning we should be at 0.019, which corresponds to that value here. The green is our lag compensated system. Now, if you do notice one thing though, is that if we were to determine the settling time of our red and green systems, there's actually quite a big difference. The settling time of our compensated system is a lot slower than of the uncompensated system. And that's because if we look at the root locus of the lag compensated system now, we do have that same pole going up and down to infinity. The asymptotes are still 90 degrees, but it's just slightly shifted now. But we now have a third pole really close to the origin. And this third pole really close to the origin has a very slow decay, meaning that while the oscillation behaviors from wow, from this, I guess like cross, because we do have a pole here, here and here. The oscillation of that system will decay faster because the negative part is larger, or it's more negative. It's not larger, but it's more negative. While this one is less negative, meaning this part will decay really slowly. And this one's a pure decay only. So because of that, we're seeing this really slow. We're seeing this green line, this really slow decay to its final steady state value. So this is what I mean by lag compensators, and PI compensators will um, significantly increase your transient response time. It's because we're adding the pole close to the origin. That's why the red system, if we were to look at the transient response time of the red system, it's going to be a lot faster. So if I were to do step info of our compensated system and compare it to step info of our uncompensated system, you can see that we go from a settling time of 2 seconds to a settling time of 20 seconds. So we do have a 10 times increase in settling time because of that hole being close to the origin. Are there any questions? I hope I'm sharing my screen. I am. Okay. So one other thing about PI controllers as well is that sometimes we might see, and maybe I'll draw this out in the lag compensator design as well. Sometimes you might see a response that looks like this, like that, where this would be our, if it weren't for that third pole, this would be our percent, this would be our peak. So I don't think the textbook doesn't define it, but I like to call it a local peak. That's like where we get that overshoot. Um, with some tuning, you can make this local peak taller like that or shorter. It's just something that to keep in mind that if you look for peak time on MATLAB, it's going to give you a peak time like somewhere up out here when it converges to its final value instead, because MATLAB is just looking at its total value. Just a little note. I wouldn't worry too much about that though. Just something that I observe is that we're just seeing the more dominant pole, which is close to the origin, showing its main behavior, I guess. All right, so that's lag compensator design. So now we can finally move on to improving the total response. So now we're going to improve the steady state error and the transient response time by combining PD and PI and lead and lag compensators together. And so we combine PD and PI controllers or lead and lag to improve transient response and steady state error respectively. So PID is called proportional plus integral plus derivative controllers. Uh, or we have lag lead compensators. So this is just the equations for it. These are the two equations for it. It's you literally you just multiply them together, because all we do is we basically put a PI controller and a PD controller in series, and then you just multiply them together. So their effects stack in that way. And same with lead and lag controllers. All right, so here I have a little bit more annotation on the this. So this is our PD controller. This is our PI controller. So then I have this D for the derivative and I for the integral. And then the D for the derivative. And when you multiply this all out, you can actually rearrange it to this form here. This is a more common form that you can formulate in MATLAB. But it's I'm just giving you both forms because that's what's given in the textbook. Now, for lag lead compensator design, the structure looks the same. So this could be the first one could be the lag, or the first one could be the lead. The second one could be the lag or the lead. It doesn't matter. It's more it's more that you want to see the relationship of the pole and zero relative to each other. So this is the lag if the pole is closer to the origin while the zero is further away. And this would be the lead if we have the zero closer, or if we have the pole to the left of the zero. Uh, one thing to note about, yeah, actually, I'll just stick with this form. There's a derivation for getting this form, but I don't think it's really necessary to show you. You just multiply it out and divide it by K3. No, why not? I'll just do it real quick. All right, so when I multiply out this controller, this PID controller, so maybe I'll write C PID, so you know it's the PID controller I'm talking about. And multiply by K S plus Z C D times S plus Z C I divided by S. So ZCI is going to be close to the origin because that's our PI characteristics. And then ZCD is going to be chosen based off of our root locus shape we want it to be in. So then we can multiply everything together and we pull out the 1 over S. And then we get S squared plus ZCI plus ZCD multiplied by S plus ZCD multiplied by ZCI. Okay, so once we get that, we can apply the K to everything, and we get 1 over S let's see. Let me think about this. Actually, we're already kind of there. So basically what you can see here is that uh, K3 is equal to K here. And then K1 is equal to K is equal to K times ZCI plus ZCD, and K2 is equal to K times ZCD multiplied by ZCI. And that's how we get this. Okay, so the design for PID controller or lag lead compensators is similar. You just combine the steps from, let's say, like for PI and PD, we just combine the steps of PD and PI controller together. And here's the steps on doing this. I used to write this out. And I used to have people copy this. It took forever. Thankfully, because of these notes, you just have it directly in your hands. So, steps towards designing a PID controller. Before I read through everything, let me just break it down into two parts or two stages. This stage is where we do the PD controller design. And the reason why we want to do the PD controller design first is because we want to change the root locus shape. we change to our desired root locus shape. Change to desired root locus shape. And that's going to affect the transient response time. Okay. Now, once we do that, we don't want to change the root locus shape anymore. So then that's when we do the PI controller design, which retains more or less preserves the uh, root locus shape. So then this preserves root locus shape while reducing steady state error. Uh, sure you can. If you really want to, you can do the PI controller design first and you reduce steady state error. Then you use the PD controller to change the root locus shape, but it just adds more angles that you have to calculate when you're doing the angle criteria check. So change your root locus shape first and then add the PI controller at the end to retain the shape. So basically, the first three steps is to design your PD controller using second order approximation. And then final you then do a simulation to make sure that your transient response design requirements have been met. Then once you do that, you can add the PI controller to reduce steady state error. It then determines your gains K1, K2, and K3. Uh, I don't think you really need to determine the gains K1, K2, and K3. You just use the gains from your PD controller to you just use the gains from your PD controller. And then simulate the system to be sure all requirements have been met and redesign if simulation requirements are not met. So we are going to go through an example on designing a PID controller for the following system where we want our peak time to be our peak compensated time to be two-thirds. It's two-thirds the uncompensated time with 20% overshoot and zero steady state error. And this is nice to design because the PI controller honestly is not that hard. We just add a pole and zero close to the origin. And then the PD is the hardest part. So first note that this is note the system type here. So this is a system type. It's a type 0. So that means ESS is constant for a step input. Okay, so because I might not give you that information, you need to deduce that information yourself. And so I guess our game plan first is we want to determine the uncompensated performance using second order approximation. So estimate uncompensated system performance using second order approximation. And so I guess when on your homeworks, so with this one and for next week's homework, because next week's homework is going to be PID and Lagley compensator design, you can just use root locus from MATLAB to determine your uncompensated system performance by finding the location of the complex conjugate poles. And I guess I'll just do that as well to show you how fast it takes and how much time you can save. Well, first of all, we just got to calculate our damping ratio because that's our first design requirement. And you're going to see that the damping ratio is going to be the percent overshoot, the natural log of the percent overshoot, divided by 100, divided by pi squared plus natural log squared of percent overshoot divided by 100. And we get 0.456. So the next step, I'm just going to write explicitly so it's more clear in the notes. Um, Find uncompensated closed loop poles where zeta is equal to 0.456 in MATLAB. So unfortunately, if you're using Python, it might be hard to find the uncompensated closed loop poles. I'm not exactly sure if there's a UI that allows you to click and choose points along that point. Um, and so what we're going to do is we're going to use the command rlocus to do that. So rlocus of G. And we're going to do that right now, real quick. I'll do it live. I'm going to do it in the command. Okay, so our transfer function is going to be transfer function of, we have s plus 8, so it's coefficient is 1 and 8. And then we have roots at -3, -6, and -10. All right, so that's our transfer function. Let me just double check that we have the correct poles. -3, -10, -6. Let's check the 0. -8, so we're good. Then I just do figure r locus of G and type in grid to turn on the grid. All right, so that is our root locus. So then we're looking for 0.456. So I look here, it's between this diagonal line of 0.3 and this diagonal line of 0.52. So I try to guess where that's going to be at. And we find it to be at, oh, we got pretty close. 4, 5, 6. There we go. Is that what I got in my notes? Yes, I have that value in my notes already. So I have a gain of 121 with a pole at minus 5.42 plus 10.6 I. The damping ratio is 0.456 and percent overshoot is 20. So that's how I find it. When I look at root locus, maybe it's the way I program my brain, but I can see that four, there are 3 poles and 1 0. So I automatically calculate in my head asymptotes at -90 degrees and 90 degrees because we have 3 poles minus 1 0. So that's 2. And then we do odd multiple of 180 divided by 2, and we get 2 unique angles of 90 and -90 degrees. Um, you got a question. Hold on. Oh, my laptop's been on mute, so you've been asking questions. I'm sorry if you asked questions I didn't hear you. I've muted my laptop. Yeah, Xander, do you have a question?
I think you can switch the screen.
I did not sh share the screen. Oh,
We
damn.
just seen MATLAB right now.
Okay. Yeah, I knew I was missing something. Do you still see my MATLAB screen? I see it on my tablet though. I'm not sure if you hold on. I got an idea. Okay. Let's try this again. Do you see that?
I still see map.
You see MATLAB now?
Yeah.
Okay. Yeah, I'll just real quick go over what I did. So basically, I just created my transfer function here using transfer function command. And from there, I got my open loop transfer function. I just put pull of G and 0 of G just to do a sanity check that I have the correct transfer function. Then I did figure and R locus. I turned the grid on. Once I did that and I plotted that, I got this. From this point on, I'm choosing my damping ratio 0.456, which is going to be right there. 456. I see that my gain is 121 with a pole location of minus 5.42 plus 10.6 I. You can see that percent overshoot is 20. So we're good. Note here that our dominant poles are the complex conjugate poles. They're the closest set of poles to the origin compared to the third pole, which is around here, which is around 121, which is around there, right? Around -8. Uh, so that's going to be our uncompensated system. So now we're going to go back to let me go back to my tablet. All right. So we found that from root locus, we found that our uncompensated poles are at minus 5.42 plus or minus 10.6J with a gain of K is equal to. So on there, it was 121, but in my notes, I have 122. It's not going to really make a difference. I'm just using 122 just because I think my numbers are based off of K is equal to 122. So I'm just going to be safe here and not deviate from my notes. Okay, so just as a iteration, like as I keep reminding you, but this term here is equal to your zeta times your natural frequency plus or minus your omega n times 1 minus zeta squared times j. This is also known as your damped frequency. Oh, yeah, you're good. So actually, and I did tell you that we do have a third pole because we're using second order approximation, and this is just more to as a note to ourselves. No, we do have a third pole. We have a third pole at P3 is equal to minus 8.17. So second order approximation will not be perfect because if we look at the pole location, -8 is not 5 times further away from -5 compared to the origin. So second order approximation is not order approximation may not be reliable due to the 5 times rule. But but unfortunately, like despite chapter 4 telling you that this is not reliable, um, this is the best we got. So it's a little bit contradictory. I don't really like it. That's why I don't really like the 5 times rule. But in the homework, if second order approximation doesn't work out and you design a PID controller and you are not able to reduce your transient response time, that's fine by me. You don't have to redesign it to meet the design requirements. If you followed all these steps and you just end up with a shit simulation, it's cool with me, you know? And especially on the exams, I don't care. On the exams, all I care about is if you can apply the angle and magnitude criteria and draw the root locus, find the asymptotes, angles of departures. It's the technique, not so much the performance. Anyway, so second order approximation may not be reliable due to the 5 times rule, but I say screw it. We just continue on. So from that, we find the peak time because we're trying to reduce the peak time by 2/3. So find TPU and TPC using second order approximation. So TPU is going to be equal to pi divided by the damp frequency. This is the second order approximate. This is a second order system performance equation from chapter 4. So that's going to be equal to pi divided by our natural frequency multiplied by 1 minus zeta squared. So that's just going to be equal to pi divided by the imaginary component of our pole, which is 10.6. And we get 0.296 seconds. So from that step, we can see that our compensated time is going to be 2/3 of our uncompensated time, which is 0.198 seconds. Okay. So using our TPC, our compensated time, we can find the natural frequency of the compensated system, and in turn, find the compensated closed loop poles. Because we're still maintaining our damping ratio of 0.5 or 0.456. Okay, so since we know that TPC is equal to pi over omega d, which is equal to 0.198. Let me write this out fully. We get that's equal to pi over omega n times the square root of 1 minus zeta squared. And we know zeta is going to be 0.456. Let me rewrite this equation, and let me write this as omega n c, so it's more explicitly clear that we're finding the natural frequency. We get pi divided by 0.198 multiplied by 1 minus zeta squared, where zeta is equal to 0.456. And we get 17.8 radians per second. Oh, sorry. Sometimes that happens, and I block the whole screen as you're copying. Okay. Now that we have that, we can find our dominant closed poles, or I'm just called the compensated poles. Is going to be at minus zeta omega n c plus or minus omega n c times the square root of 1 minus zeta squared j, which is equal to minus 8.13 plus or minus 15.8 j. All right. Another, I guess, if you were to poke my brain on a sanity check right now, one thing that I check when I do this calculation is, and actually I only do it when I teach this class because I'm constantly trying to check for mistakes I make on my notes. Damping ratio is constant, meaning that our ratio of rise over run is also going to be constant. If you look here, I can see my real component is roughly -5, and my imaginary component is 10. So I have a run of -5 with a rise of 10, which is roughly 1/2 ratio. Here we're roughly maintaining that ratio where we have a rise of almost 16 with a run of -8. So in my head, I'm like, okay, we're good because our damping ratio gives us this ratio of rise over run, because and that's roughly the same. So in my head, I'm just doing these little calculations as sanity checks to make sure that we're on the right track. Okay. And the reason why I do this is because when we work on problems this long, it's really easy. If you make a mistake here, it just propagates all the way down, and it's just hard to, I mean, you have to go back and redo it if you catch it. And if not, uh, it's just going to be a lot more work. The earlier you can catch these mistakes, the better, but sometimes it's not always the case, and that's okay. I will work with your mistakes, and that is okay. So then now we're going to design the PD controller. So we want our root locus to pass through this point. Want root locus to pass through this point. And I'm sorry if I sound like a broken record when I keep saying this. It's just because there's so many steps. I just want you to keep all of this in mind. So we're going to design the PD controller. Design the PD controller such that the root locus passes through minus 8.13 plus or minus 15.8J. All right. And so the PD controller is defined as, maybe I'll write it as CPD here. Going of S is defined as KPD multiplied by S plus ZC. ZCD now, because now that we're adding a PI controller to it, I'm going to differentiate the 0 for the PD and the 0 for the PI controller. And we're going to apply the angle criteria to determine the location of where ZCD needs to be at. And we're going to do that next time. And I'm going to stop for today and let you all finish copying this. So we'll pick this back up tomorrow. I know it's a long day. It's a long night.
Is that, PPD?
Yeah.
See the gain that we pulled from the root locus before? Or that be a
No, it's going to be a different gain. So the question was like, will the KPD we use be the gain we used from earlier, which is 122? No, it will not be. It's going to be different. But once we find a KPD, we then use that for the PI part as well, because the PI preserves the root locus shape. So if we use that same gain around 122, it's going to put us more or less within that ballpark of the closed loop pole. Yeah. Yeah. You can use a new gain value if you want once you design the PI part. You're gonna just find that's very close to it's gonna be very close to the gain of the PD controller. There's gonna be a lot of nuance in choosing gains, and I'll show you multiple scenarios in which the gains can vary a lot, even though we can get the same result. And I'll talk about that tomorrow. Yeah.
About like PD and PID design in general, like
Yeah.
you show the examples of like the circuits that act as PID controllers.
Yeah.
Do you ever use those, or is it mostly just digital?
It's mostly digital.
Okay.
Yeah, yeah. Those are just like when we had analog systems and not digital systems, and even computers back then were big and bulky. That's what they would use. Not we, they would use. I've never used that before though.
But it's just all the digital stuff now.
Yeah, this is all digital stuff. The reason why I just show it is just because people are like, what does a PID controller look like? I'm like, well, actually I have it at the bottom of the slide here. What does it look like? That's what it looks like. And I really don't want to do a block diagram or design like that. So I'm like, forget that. But with digital systems, you can I guess equivalently take the derivative and equivalently take the integral in digital systems. You don't actually take the continuous time, you do it in discrete time, but it's close enough to the real thing. Yeah. I mean, if you want to like derive this is like, I'm pretty sure it's not hard for someone that back in the day worked on this, but when I look at it, my brain's like, no. Yeah, no problem.